So in this video, I'm going to recap couples and also equivalent systems. So first up is couples. So couples can be referred to by other names. So sometimes they're referred to as couple moments or just simply as moments. Okay, so all of these things mean exactly the same. So couples are caused by two equal and directly opposite forces. Okay, so for example, a couple would be created when I had a force going this way, which I'll call Fc, and one going back the other way, also size Fc, but obviously in the opposite direction. Okay, so the resultant force of this couple is 0, so only causes rotation. Okay, so the two forces cancel each other out, and all that happens is this thing tries to cause rotation about whatever body it's applied to. So the classic example is a steering wheel, where you would apply a force on one side of the steering wheel, a force on the other side of the steering wheel, and you'd cause it to spin round and round and round. So if you want to calculate the size of a couple, it's very straightforward. I'm going to call it MC for moment of a couple. And it's going to be equal to, I'm going to call it Fc, since that's the notation I use here, the magnitude of the force, and it's multiplied by the separation distance, which I'll call DC. Okay, so for this example, that is your separation distance. And just like when we were looking at other, regular moments created by forces about points of interest, it needs to make sure that the DC is the perpendicular distance. So if you drop a perpendicular line between those two forces, that distance of that line is what you're looking for to apply this equation. So that's pretty much all there is for couples. I guess the only other thing is that you are still going to have a direction associated with the couple. So this one here is going to try and create a, clockwise rotation about whatever body it's applied to. You can think of it like, these working against each other is going to try and spin it round and round clockwise. Obviously you can have anti-clockwise couples. If you swapped over the arrows on these, you would produce one. So that's pretty much all there is on couples. So the other topic that I'm going to talk about in this video is equivalent systems, which also use this couple type thing. Alright, so there's two types of equivalent systems that you might be asked to show. So the first type, is when you're asked to do a simplification to a force and couple. Alright, so you're asked to simplify all the loading on a system to just a force and couple acting through the point of interest. Okay. There's a second option, which is slightly harder, and this is when you want to simplify down to just a force acting at an equivalent distance from the point of interest. Okay, so let's give a quick example. So let's pretend that we started out with a system that looked like this. I don't know, just making one up. We'll call this point O our point of interest. Okay, and we're going to have a few different forces. Let's call it F1, F2, F3. Okay, so if we wanted to make an equivalent system, what we do is we need to take all of the different loading on this, and we can also have couples acting as well. Let's pretend we have a couple acting here, M1, and we need to put all of them onto point O for the first type of system. Okay, so what it might look like So instead of all these forces in moments, we're going to end up with one resultant force. Let's call it FR, which is the equivalent of adding all of these forces together. And we're also going to end up with a moment, okay? And I'm going to call it MRO. And that's the equivalent of adding up all the moments created by these forces, as well as any couples, which is like this M1, applied to your system. All right, the second type of system, or equivalent system, I should say. So this time we're only going to simplify onto one force, but it's going to act at an equivalent distance from the point of interest. Okay, so again, if our point of interest was still O, this time our resultant force would be offset some distance, I'll call it D, from point O, and this resultant multiplied by this distance, the perpendicular distance, has to be equal to the moment from our previous system. Okay, so these are the two different options. The only equations that we need to be able to do this simplification is that the sum of the moments about our point of interest, so I'll call it O, is equal to MRO. That's going to give us this value here for the first system. And it's also going to give us a hint at what the distance needs to be for the second system. The other equations that we need is that the sum of the forces in the x direction is equal to the resultant in x, like we were doing last week. And the sum of the forces in y is equal to the resultant in y, again what we were doing last week. So from these two equations, you should be able to work out your resultant force. So I'm going to do an example of it in the videos. Hopefully, again, that will be able to clarify any understanding in actually applying this theory. So I'll see you in those videos.